So continuing with Unit 3, now we're actually going to get into writing proofs. Okay, so everything we've talked about so far has kind of led us up to this point. So now we're actually going to get into writing proofs about two things being equal to one another. Okay, so before we get into writing proofs, we need to remind ourselves of a few definitions that we saw back in Unit 1. Okay, so first up is the definition of congruent. We say that two things are congruent to one another. In this case, we're talking about segments. So if we have two segments that have the same length, then we would say these two segments are congruent to one another. Okay, and we could write this in two ways. We could either say right here, this statement is saying that segment XY is congruent to segment AB, or we could say this segment right here without the line over it. This is just that XY is congruent to AB, meaning the lengths are congruent to one another. Okay, next up is the definition of a midpoint. So given this picture right here, a segment with a set endpoint, a set midpoint, we can say that if D is the midpoint of this segment CE, then CD, this half, is congruent to DE, this half. Okay, so midpoint just splits a segment into two pieces. Okay, and then lastly, we have the segment addition postulate. Okay, so the segment addition postulate, if I've got a segment, this time our segment is PR, and then I just randomly mark a point somewhere on this segment. It doesn't necessarily have to be in the middle. I just randomly pick a point. So I picked point Q right here. Then the segment addition postulate tells me that if I take the length of PQ and the length of QR and I add them together, it will equal the length of my whole thing, PR. So that's what our segment addition postulate tells me. So now that we remind ourselves of a few of these definitions, let's get into it. So if we are looking at this first one, okay, so this first one right here, this is on page 1. So we're asked to prove the following, and we're going to write a 2-column proof to show it. If AC is equal to DF and AB is equal to DE, then BC is equal to EF. Okay, so starting out, we've got these two statements right here. So we have to start out with our given statement. So that's anything between the if and the then. So that's why they started out by writing in all of the statements that you're going to have to deal with. So they gave us the statements. We need to fill in the reasons. So the first statement they gave us was AC is equal to DF, AB is equal to DE. We'll have to look up here in our sentence in our conditional statement. AC equal to DF, AB equal to DE. That is our hypothesis. That's going to be our first statement. Okay? And our reason for having that is that it was given to us. Okay, so next up. So eventually we're trying to work our way down into BC equaling EF. And if we look down here at the bottom, our very last statement is BC is equal to EF. So with these proofs, if nothing else, you always know how to begin it and how to end it. You'll always begin by putting your hypothesis as your first statement. So everything between if and then will be your first statement. Your first reason will always be given. And then you know that your last statement is going to be your conclusion, or the stuff between the then and the period. So BC is equal to EF. So starting out with just AC is equal to DF and AB is equal to DE, eventually we know we got to get a BC and an EF in there. Okay, so if we look at their next statement that they gave us AB plus BC is equal to AC, and DE plus EF is equal to DF. So we have to ask ourselves, how in the world did they get these two statements? Well, if from my conditional statement I'm not really getting anything, let me look at my picture. Okay, so does this picture help me make any sense of this? Okay, so we say AB, that's this piece right here, plus BC, that's this piece, is equal to AC, that's the whole piece. Well, that kind of looks like segment addition postulate. Let me look at the next one. DE, that's this piece, plus EF, that's this piece, is equal to DF. Well, that's also segment addition postulate. So it seems that these two statements were created from using the segment addition postulate. So that's going to be our reason for having those two statements. Let's look at our next one. AB plus BC is equal to DE plus EF. Okay, so I've got some pieces in there that look familiar. Okay, so I've got a AB plus BC here. I've got an AB plus BC right here. I've got a DE plus EF right here and a DE plus EF right here. So for some reason, they set those two equal to one another, even though up here they're in two different equations. So I have to look back at my very beginning. So the very beginning told me that AC is equal to DF. That's what it told me in my very first statement. And then if you look in our second statement, we further expanded our definition of AC and DF. So AC is equal to DF. We said AB plus BC is equal to AC. DE plus EF is equal to DF. So we have AC and DF here and AC and DF here. So all they decided to do was they took this first part of my first statement, AC is equal to DF, and they came down here and they rewrote it. But they rewrote it using the new values that we learned at step 2. So at step 2, we learned that AC was equal to AB plus BC, so that's why they wrote it here. We learned that DF was DE plus EF, so they wrote it here, and they set it equal to each other, and now we've got a brand new equation to look at. Okay, so let's keep moving. So now we've got AB plus BC is equal to AB plus EF. Okay, so if you look between statements 3 and 4, there's only one thing that changes, and it's right here. This DE becomes an AB. Okay, so how could they just make that switch out of nowhere? Okay, it doesn't show anywhere up here in my conditional statement, up here in my picture. So how in the world could they make the switch for AB and DE? Well, again, if we look back at our very first statement, we see that they said AB is equal to DE. So anywhere that there's a DE, we can replace it with AB, and anywhere there's an AB, we can replace it with DE. So that's exactly what they did. So they took right here and they just switched out the DE for AB and gave us this fourth statement. Okay, and then lastly, eventually we know we're trying to get down to BC is equal to EF. And so we need to look and see how can we figure that thing out? How can we get to that point? And so they both have an AB, so let's just subtract the ABs. So we subtract ABs, it gets rid of it over here, gets rid of it over here, and I'm just with the BC is equal to EF, and we were able to get that by using the subtraction property. All right, so let's look at the next one. Let's look at page 2. So page 2, we're given this figure, and we're told given that LK is congruent to NM, KJ is congruent to MJ, we need to prove that LJ is congruent to NJ. Okay, so if we look in our triangle right here, we know exactly what they're talking about when they're using all of these different segments. So, again, they gave us most of our statements. We need to go through and fill in the reasons. Okay, they didn't give us our very first statement, but we know exactly what that first statement is going to be. If we look at our conditional statement right here, our first statement on our proof should be our hypothesis. Okay, so either they're going to give it to you in a case of over here where we had an if-then statement, or they're just going to tell you that this is your given, this is what you're proving. So your given, LK is congruent to NM and KJ is congruent to MJ, that's going to go in your first statement, and that's given to us. Okay, likewise, just how over here, the stuff between the then and the period, our conclusion, that was our last statement. Right here, this part right here, LJ congruent to NJ, that's what we're setting out to prove. So that's our proof statement or our conclusion. So that's why we'll put it last here as well. Okay, so let's work through this thing. Okay, so we've already got our first statement. We got our first reason. So they give us NM plus MJ is equal to NJ. LK plus KJ is equal to LJ. Okay, so that looks kind of similar to one we saw over here. So let's just check and make sure. If we're looking at our picture, NM plus MJ is equal to NJ. And then LK plus KJ is equal to LJ. Okay, so both these are example of the segment addition postulate. If we have a great big long segment and we cut it into two pieces, then the length of those two pieces added together will equal the length of my whole. So the reason why I have this segment right here is because of the segment addition postulate, and I just abbreviated it to SAP. Okay, so let's keep going. So now we have NM plus MJ is equal to LJ. Well, if we look up here, we've got NM plus MJ is equal to NJ, but we don't have, but here they put it as NM plus MJ is equal to LJ. So that's weird. How were they able to make that switch? So first you might be thinking, well, did they somehow make the switch of NJ and LJ? But if we look up here, I mean, we've got nothing to provide us with that evidence. But what we do have, in this first statement, we're told that LK is congruent to NM. and we're told that kj is similar to mj. So we look at the things on the left side. Lk became nm, okay, and it says up here we can switch those out anytime we want. Kj and mj, again, we can switch those out anytime we want. So to get from here to here, they basically took this second part of statement 2 and rewrote it by subbing in the value. So nm plus mj is equal to lj. We got that from using substitution property. Okay, then we have nj is similar to lj. Okay, so again, we're not really sure how we got that. So let's look and see how did they do this becomes that. Well, if we look back at our second statement, nm plus mj is equal to nj. So now we're going to use the first part of our statement 2, and we're going to use it here. So anywhere that we have nm plus mj, we can replace it with nj, which is what they did right here. Okay, so they got statement 4 by using substitution property as well. Okay, and then lastly, if we look back up here at our proof statement, they wanted us to have lj is congruent to nj. And so all we're going to do is to get from here to that point, to get there, is we're just going to switch the order. And we're going to switch the order using our symmetric property. Okay, so now on page 3, we have got this proof. If hj is equal to ik, then hi is equal to jk. All right, so we were given the if-then statement. So our first statement should be our hypothesis, everything between if and the comma. So our first statement will be hj is equal to ik. And that reason for us having that statement is that it was given to us. Okay, I know eventually I'm going to need an hi and a jk. So I need to get those pieces in there. So they gave us this as our second statement. Hi plus ij is equal to hj. And ij plus jk is equal to ik. When we look up here in our picture, we've got hi plus ij is equal to hj. Ij plus jk is equal to ik. So they use the segment addition postulate to get both of these statements right here. Okay, so let's keep moving. Next up, we have hi plus ij is equal to ij plus jk. Well, we have an hi plus ij right here. We have an ij plus jk right here, but they're separate up here. So we have to think, how were they able to combine those into one equation? Well, if we look back at our very first statement, we have that hj is equal to ik. Okay, and then down here, in the second part, we just went and further expanded our knowledge, our definition of hj and ik. So all they did here is they rewrote our original statement, hj is equal to ik, by subbing in the values for hj and ik we learned here. So if you would, this is our original hj, and this is our original ik. So they just took this statement and rewrote it. Okay, so they got that by just substituting in the values that we learn at step 2. So we got this statement right here by using substitution property. And lastly, the one that I'm trying to get down to is hi is equal to jk. Well, if I look up here, both of these have got an ij. So if I want to get rid of the ij's, I'm just going to subtract them. So I got this last statement, hi equals jk, by using the subtraction property.